Hello, Matthews. Gatos here. In this video, we're going to cover the infinite limit of rational functions. Let's get started. First of all, let's just talk about investigating what a rational limit is and an infinite limit. So for example, if I have this limit here of this number sequence, a half, a quarter, an eighth, 1/16, etc., that means it goes to infinity. Let's look at what's happening. First thing I notice is that my numerator is always 1. My denominator, if you look, it's doubling. It's getting bigger and bigger and bigger. So as I approach an infinitely big number, I'm going to have 1 over a bigger and bigger number. That is going to approach 0. So the limit of that sequence would be 0. Let's look at another one here. So in this one here, I can see that my denominator is getting bigger, but so is my numerator. If you look at this numerator getting bigger, this denominator getting bigger. Look at the relationship between the numerator and denominator, however. If this is 1, 1 more is 2. When this is 3, 1 more is 4. When this is 7, 1 more is 8, etc. So whatever my number in the numerator is, we'll call it x, my denominator would be x plus 1. So you can see that those are getting closer and closer to a value of 1, although never reaching it. To get 1, I would have x over x, but I don't have x over x. I have x over x plus 1. So this limit is approaching a number of 1. It'll never truly get there, but that's where the limit is going. This one here. So we can see that it's getting bigger, but something odd is happening with the signs. So if you look at here, 1, 9, 25, the next one would be 49. Those are all perfect squares, positive perfect squares. Look in the other ones though. These are all negative numbers, also perfect squares. That next one would be negative 64. So you can see the positive ones are getting bigger and bigger. They're going towards positive infinity. The negative numbers are getting bigger and bigger in the negative direction. Those are going to negative infinity. Since they're not approaching the same value, we can say that the limit here does not exist. Let's look at how do we estimate numbers, limits numerically. We've looked at sequences, now let's look at limits numerically. So I'm going to take this function f of x and I'm going to look at it 3 different ways: numerically, graphically, and algebraically. So let's say we wanted to figure out the limit as x approaches infinity. Now we can't just sub in infinity because it isn't a number. But what I can do is sub in x values that get bigger and bigger. For example, 10, and then 100, and then 1,000. And I just keep getting bigger and bigger, approaching infinity. And I want to look at what's happening to my function or my y value. So when I substitute 10 into the equation here, I end up getting a value of 12.5. When I sub in 100, I end up getting 10.2. And I keep doing the number crunching for each one of these numbers. So I can see that x is approaching infinity and the function, the y value itself, is approaching a value of 10. So I know that the limit is 10. Let's look at that graphically. So here's that function f of x, and here's the graph of it. So you can see the graph is split into 4 sections by the asymptotes, and I want to know what happens as x approaches infinity. So here's my x value here. I'm just to the right of 2, and as I approach positive infinity, I get bigger and bigger and bigger. You can see that graphically, my graph is going towards a y value of 10. And that's because at y equals to 10, we have a really special part of the graph called the horizontal asymptote. So I've seen numerically and graphically that the limit is 2. Let's look at it algebraically. Now, if we look at something algebraically here, we know that the denominator and numerator is going to get really big as x approaches infinity. It's going to get infinitely big in the numerator and the denominator. So what I want to do is I just want to eliminate x. And I want to know, focusing in on the constant parts, the parts that aren't tied to x, what is happening with this function? The reason that I do this is because I know the limit as x approaches infinity of c, where c is any real number, is just the constant value itself. I'm going to use this to help me solve for it algebraically. So for example, in this limit here, I want to take x out of the mix entirely. So I'm looking at the limit as x approaches infinity. Let's factor an x out. So 10x divided by x is 10. And in the denominator, x divided by x is 1. 2 divided by x is 2 over x. So now I've got rid of my x values. I can look at the limit as x approaches infinity of 10 over 1 minus 2 over x. So let's look at this here. Right now, what I have is only x in one place right here. So what's going to happen as x approaches infinity, as I get bigger and bigger in my x value, that makes the denominator of this fraction bigger and bigger. And I know 2 over a really big number is going to approach 0. So I know the limit as x approaches infinity of this is going to be 10, constant value, over 1 constant value minus 0, which is just 10 over 1 or 10. So my tip here is that factoring out an x is really the same as multiplying by 1 over x. The reason I multiplied by 1 over x is because that was the highest degree of x. So here's my tips on how we're going to find these limits algebraically. We know if we have the limit as x approaches infinity of 1 over x, where x is the denominator, that is going to approach 0. So as the denominator gets bigger and bigger and bigger, the entire fraction, 1 over x, approaches 0. This is called a bottom-heavy function. So functions approach 0 as x approaches infinity. That's what a bottom-heavy function is, when x is in the denominator. Well, if 1 over x goes to 0, then 1 over x to any power also goes to 0. So we're going to use these two limits to help us solve any rational limit. So what we're going to do is multiply the numerator and denominator by 1 over x to the highest power so that we can use rules 1 and 2 to help us. So I have 3 examples for you. In my first example here, limit as n approaches infinity of 1 over n plus 7. First thing I look at is what is the highest degree, and that's n to the 1. So I'm going to multiply numerator and denominator by 1 over n. So in doing that, I have the limit as n approaches infinity, 1 times 1 over n, over n times 1 over n, plus 7 times 1 over n. So I know from my bottom-heavy definition that this, as I get infinitely big in the denominator, will go to 0. This, as I get the denominator bigger and bigger, will also go to 0. So I'm left with 0 over 1 plus 0. So that means the limit as n approaches infinity of this function here, the whole limit will just go to a value of 0. Let's try this one. The limit as n approaches infinity of this one. So looking at all of my variables, I see that my highest degree is n squared. So I'm going to multiply top and bottom by 1 over n squared. So in my numerator, I'll have the limit as n approaches infinity distributed in. So 3n squared times 1 over n squared is 3, plus 40 times 1 over n squared, all over distributing this one in. 1 over n squared times 4n squared, 2n times 1 over n squared, and 9 times 1 over n squared. So I know this bottom-heavy function, as n gets bigger to infinity, approaches 0, and both of these also approach 0 as well. So my limit is going to be 3 plus 0 all over 4 plus 0. So the limit altogether as n approaches infinity is equal to 3/4. Okay, let's try another one. In this last example here, my highest degree is n to the exponent of 1. So I will multiply top and bottom. Oh, I lied to you. It's actually n squared. Let's multiply top and bottom by n squared. So that's the limit as n approaches infinity distributed in. So 1 over n squared times 2n squared is 2, minus 5n times 1 over n squared is 5 over n. All over 7n times 1 over n squared is 7 over n. So this bottom-heavy function goes towards 0. This bottom-heavy function also goes towards 0. So my limit is 2 minus 0 divided by 0. Now that's a problem. I can't divide by 0. So what that means is that my numerator is going to grow bigger and bigger. I can't account for that, making the whole limit not exist. It's not going to approach a specific value. Now, this should sound really familiar. It should sound like a horizontal asymptote. Let's review that. Horizontal asymptotes are horizontal lines, which means that they are y equals lines, that the graph of the function approaches as x approaches positive and negative infinity. Doesn't that sound like a limit? As x approaches infinity, where does y approach? That's really what a limit is. In fact, horizontal asymptotes, by their definition, is where the ends of a graph approach. That's also the limit definition from a graphical perspective. So if we can remember horizontal asymptotes from 30-1, we can use those for calculus. So here's the 3 different scenarios when I have horizontal asymptotes. First one is when the degree of the numerator equals the degree of the denominator. In that case, the horizontal asymptote is a ratio of the leading coefficients. So you can see here, these are both linear. So since they are both degree 1, I can look at the ratio of the leading coefficients, and I know the horizontal asymptote is 2/3. In my next example, the numerator degree of 0, is less than the denominator degree, which is 1. So degree of 0 less than degree of 1, when that happens, the x-axis will always be the horizontal asymptote. The third type of horizontal asymptote is when I have a top-heavy function. So this one here is called the bottom-heavy functions because the denominator is bigger and it'll always equal 0. These ones here are called top-heavy functions, which means that the degree of the numerator is bigger than the degree of the denominator. In that case, there is no horizontal asymptote because it's just going to grow bigger and bigger without bound. So we can take that idea and apply it to limits. So same thing, limit as n approaches infinity. When the degrees are the same, top and bottom, the limit will be the ratio of the leading coefficients. In this example here, if the degree numerator is bigger, see n cubed is bigger than n squared, in that case, I know that the limit does not exist. And the third scenario, if the degree of the numerator is smaller than, or the denominator degree is bigger, the whole limit goes towards 0. So this limit would be 0. Again, this is a top-heavy function. This one here is a bottom-heavy function. So if you can remember the rules of horizontal asymptotes from 30-1, you can use those rules when it comes to limits. So remember, the limits in this lesson go to infinity and beyond, just like Buzz Lightyear limits. So I hope this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.